would like to thank you for inviting me here to talk to you, and in particular to Professor Janusz Wolny, an old friend who convinced me to come here. And it's not my first visit. I've been here several times at Professor Wolny's invitation. The subject of my talk is quasi-periodic materials, a paradigm shift in crystallography. I'm from the Technion, Haifa, Israel, and also I have a position in Ames, Iowa State University. So let us start. In the mid-80s, there were 3 surprising discoveries on the structure of matter and its properties. And these discoveries came year after year, and all 3 of them received a Nobel Prize later on. First online was my discovery of quasi-periodic materials, and the names on the first publication was my name, Ilan Blech, Denny Gratias, and John Kahn. I'll tell you later about their role in the publication. Next came the discovery of fullerenes, and Harry Kroto and his colleagues discovered that, and last 1986, high-temperature superconductivity. When high-temperature superconductivity was discovered by Alex Muller and Bednorz, nobody was against it. Everybody was happy. Hey, we have a high-temperature superconductivity with some benefits. When fullerenes were discovered, Harry Kroto told me that he had 6 papers against his model, but his model was accepted very soon. But when quasi-periodic materials were announced, they met a lot of rejection, objection from the top of the scientific community. And later on, I'll tell you how it happened. I will start by introduction so that everybody will know what I mean when I say order, periodicity, and rotational symmetry. This is crystallography. So this is a 2-dimensional model, and it is clearly ordered. What does it mean to you? If I ask you to continue it in every direction, you know how to do that. That's order. There's also periodicity. You see, if you follow this red line, you see that there is equal distances between points. This is periodicity. Because this 2-dimensional structure is periodic, there is periodicity in every direction. Also in this direction, periodicity. That's all. What about rotational symmetry? I can rotate this 4 times. 1, it looks the same. 180 degrees looks the same. 270 degrees looks the same. Back to 0, it looks the same. I can do it 4 times and it looks the same. This is why this structure has a 4-fold rotational symmetry. That's all. Crystallography. Skip what's written. The old Greeks knew something about crystallography, which is amazing because ancient people knew nothing about science. But about crystallography, they were right. They assumed the structure is built of very small particles. They called it atoms, Greek. And these particles are arranged in some order. And this is why crystal has facets on them with angles that you can measure. But nobody could prove that the idea was right until 1912. Von Laue, German scientist, performed the first X-ray experiment. And we had a tool to study crystals. A year later, Bragg, the father and the son, came up with the Bragg equation, and voila, we have a science. And this is the beginning of the science of crystallography. Now, over time, because all the crystals that were studied were ordered, and therefore crystals, but they were also periodic. Hundreds of thousands of different crystals were studied, and they were all periodic. And so, a definition came from these observations, and the definition looks like something like this. This is from a book, X-ray diffraction by quality. A crystal is a solid composed of atoms arranged in a pattern, periodic in 3 dimensions. Very simple definition of a crystal. Another definition from a book by Bart and Masalsky says atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. The same meaning, different words. Okay, so what is a crystal? It's a solid material in which the atoms are ordered and periodic. Life was simple, and the science of crystallography developed mainly because of the development of the machines of the X-ray diffractometers who could give us better and better and better and more precise results. This was the science. I studied from a book by Charles Kittel, and it's called Introduction to Solid-State Physics. I marked something in green. I know you cannot read it because it's small. I enlarged it for you. And it says the following. We can make a crystal from molecules, which individually, each one of them, have a 5-fold rotation axis. The molecules can have 5-fold rotation axis, but we should not expect the lattice to have 5-fold rotation symmetry. Why so? Because in periodic structures, the allowed rotational symmetry is 1, 2, 3, 4, and 6, no 5, and nothing beyond 6. This was true, it is true today too. Periodic crystals cannot have 5-fold rotational symmetry, and life was simple. Now here is an example of atoms in diamond. These are carbon atoms in diamond, picture I took many years ago by high-resolution microscopy. And you see that there is order, and you see also that there is periodicity in this direction, and in this direction, and in this direction, any direction. And the rotation symmetry is allowed. 1, 2, 3, 4, 6, no 5, nothing beyond 6. Now let's go to a reciprocal space. This is a space in which the diffraction pattern occurs. This is a diffraction pattern taken by an electron microscope. The main point in the center is the transmitted beam, and all the other points are diffracted beam taken by transmission electron microscopy. Because this diffraction pattern was taken from a periodic crystal, the diffraction pattern is also periodic, and there is periodicity in each and every direction. This direction, in this direction, in this direction, you see periodicity. The crystal is ordered and periodic, so is the diffraction pattern, ordered and periodic. Very simple. Rotational symmetry is allowed in the reciprocal space, also 1, 2, 3, 4, 6, no 5, and nothing beyond 6. And then something shocking happened in the science of crystallography. And I'm going to say something about the science of crystallography. The science of crystallography has a union. It's called International Union of Crystallographers. It is composed of mathematical crystallographers. These are hardcore mathematicians. Everything has to be defined from the very foundation. Everything is very strict. And they came up in 1991 with a new definition for a crystal. And the new definition sounds like a poem. I will show it to you, and I'll show you how poetic it is. So this is the new definition of a crystal. It doesn't say a crystal is. No. So, by crystal we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal we mean any crystal in which three-dimensional lattice periodicity can be considered to be absent. What? A song, a poem from the International Union of Crystallography of those mathematicians? What happened? Number one, that we need a new definition, and number two, why is it so soft? And here is the story. And the reason is the discovery of quasi-periodic materials. 1982 was the 70th birth of crystallography. You remember, von Lauer in 1912, 1982, my discovery. And this was the year quasi-periodic crystals were discovered. To show you what happened in the afternoon of the day of the discovery, I will show you my notebook from that day. And sometimes, this is not these people, you are experienced scientists, each one of you, but sometimes I talk to students, and I tell the students, and you can tell your students too, every experiment or every calculation you make, write it down in a logbook. You may remember it next week, but not 30 years later. It is important that it is in a logbook. This logbook was very essential in my career. This is one volume of many volumes of transmission microscopy work, and it contains a lot of information. I can tell you that when my discovery became famous, it was done at the National Bureau of Standards. They took this booklet to count the pages and to see, this is an official notebook, to see that every little binding contains 16 pages exactly, that I did not add anything and I did not take out anything. Okay? This is a document. All right. The date is April 8, 1982. I was working on aluminum 25 weight % manganese. This is rapidly solidified alloy that I have prepared in the laboratory. And I studied the phase structure of this material. It's a long story why I study this. It's one of a series of many, many alloys that I studied. So you see plate number 1720 is SAD. SAD is diffraction, selected area diffraction pattern. 1721, another one, 1722, picture magnification 28,000 times, and so on. And then I arrive at the picture number 1724, 36,000 times magnification. I will show you this picture. I look at this picture and I say, hey, what's going on here? Very strange. I will show you, I'll explain why it was strange. Then I say, okay, I take a diffraction pattern from one of the crystals, 10-fold rotation symmetry, impossible. And I write in bracket 10-fold with 3 question marks. This was the discovery. This is it. It's in the afternoon of April 8, 1982. And in the Nobel Foundation, they said it's very rare that you can pinpoint a discovery to an hour of a day. Okay, and then I continued that afternoon to make many experiments to find out what I have. I thought that I have a twinned structure. And I was looking for the twins. And I could not find them. There were no twins there. And I was a very experienced transmission electron microscopist. If I couldn't find them, they were not there. I was sure. In day one, I knew that these are not twins. It's something else, but not a twinning. This is Archimedes. When Archimedes discovered his law of Archimedes, the legend tells us that he jumped out of the bathtub shouting, Eureka! We don't do that anymore. Today, when you make a discovery, usually you say, wow, that's interesting. Oh, what's going on here? Strange. Okay. This is the picture, 1724. You see the small crystals here. If you look down at the left down corner, you see half a micron bar. And you see these are crystals about half a micron to a micron in size. Nothing very special. But what caught my attention was that some of these crystals are pitch black. On the left, you see some of them are black. Now, when a crystal is black, in bright field image for the electron microscopy to run you, it means that most or all the energy goes to the diffraction. And I have never seen a crystal that diffracts so heavily so there is no intensity in the transmitted beam. And then I said, well, take a diffraction pattern. I took a diffraction pattern from one of these black crystals, and this is it. I look at this diffraction pattern, and I say, wow, what's going on here? And I start to count the rotation symmetry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, cannot be. 1, 2, 3, 4, 5, 10-fold. And I write in my logbook 10-fold rotation symmetry. But that's not all. You see, there is no periodicity in this diffraction pattern. Look at this line. You see, along the red line, there is no periodicity. The ratio of distances, instead of being 1, 2, 3, 4, and so on, turns out to be the Fibonacci number, which is an irrational number, with a Fibonacci number tau, also called the golden mean, and, oops, sorry. Okay. But let's continue. That diffraction pattern was only one, but in the microscope you can rotate your specimen and you can tilt it, so you can get to any orientation you want. And I took diffraction patterns of all the orientations. So you see, if you count from the right bottom upwards, it is 5-fold, 2-fold, and 5-fold again. And down there it's 5, 3, 2, 3, diffraction pattern. And you see the angles between them. I measure the angles between the rotation and the tilting. This symmetry is icosahedral symmetry, and I will show you shortly what an icosahedron is. This is what I thought I have. These are twins in diamond. We cannot dwell on that too long, so we just skip it. But these are the twins that I thought I have. I could not find them. 1984, the discovery was made in 1982 at NBS, National Bureau of Standards, when I spent my first sabbatical. Then I came back to the Technion, met the first person who was willing to work with me. His name is Ilan Blech. He was a professor at the Technion and left shortly after we published his paper. And we sent this paper for publication in Journal of Applied Physics. Well, you know, those days, scientists could not type those days. We had typists in the office. They had typing machines. They typed our papers. For the young among you, it sounds very strange. My generation, it's natural. Now we can all type. So a secretary typed this paper for me. I corrected it, she typed it again. I corrected it, typed it again. Finally, put it in an envelope, stamp, address, send it for publication, Journal of Applied Physics. In 2 weeks, it was rejected on grounds that it will not be interesting for the community of physicists. So I sent it to a metallurgical journal called Metallurgical Transactions, and it was accepted and published. But it was published I sent it in October of 1984. It was published in June of 1985, very long publication. In the meantime, I came back to NBS for the summer. I was there every summer. My host, John Kahn, a famous material scientist and thermodynamics expert, proposed to me, hey, let's do something else. Let's publish a short paper, only your discovery, without the Ilan Blech model, and send it to a quick publication, and I agreed with him, and we sent it to PRL, Physical Review Letters. It was published in 2 weeks, and when it was published, hell broke loose. From all over the world, I started to get emails, telephone calls, Danny, we have it, we have it. And in a very short time, a large community of avant-garde young scientists took my discovery and turned into a flourishing science that continues until today. And Janusz Wolny was one of the youngsters. What is icosahedral symmetry? This is an icosahedron. And the angles between, you see, if you look from up down, you see there's the 5-fold rotation symmetry. It's not the only one. On the side, you see also 5-fold rotation symmetry. Okay, so this is why we called it the icosahedral phase, because it had icosahedral symmetry. Enough of that. You can also show icosahedral symmetry on the football. You have a good football team here in Krakowie? You win some games sometime? Okay, if you do, I promise you, they don't know that they play with icosahedral symmetry. They don't know that. Okay, let's go on. What is quasi-periodicity? To start, let's go to Leonardo Fibonacci de Pisa, the greatest mathematician of his time. This is a drawing of him. This is a picture of a statue, actual statue, that was erased for him just behind the inclined tower of Pisa. If you visit the inclined tower of Pisa, behind it, there is a graveyard under a roof. He is not buried there, but this statue is there in his memory. To understand quasi-periodicity in one dimension, we have to understand Fibonacci rabbits. So what is Fibonacci rabbit? In the first month, we have one female rabbit. She has a husband or a boyfriend. They come to visit. She has a baby. In the second month, she has a baby rabbit. In the third month, the mother has another one. The baby has to mature before it can reproduce. So, in the first month, we have one rabbit. In the second month, 2. In the third month, 3. In the fourth month, we have 5, then 8, then 13, 21, and so on. I stopped because it was the end of the page. The numbers on the left are called Fibonacci series, or Fibonacci numbers. they have two characteristics. Number one, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8. This is the rule. Also, if you go to infinity, divide the number of orbits in the last row by the one before, you arrive at the Fibonacci number, which is the number tau, which is the second equation, number tau, 1 plus root 5 divided by 2, which is 1.618. It's also called the golden mean, and people who claim that they understand aesthetics, and they claim that you do not understand aesthetics, these people will tell you that this number is the golden mean. It has some unbelievable characteristics. You better not argue with them. But this is the Fibonacci number. So what is quasi-periodicity? Look at the last row. You see large rabbit, small rabbit, large, large, small, large, small, large, large, small. There is order. Fact is, if you follow the rules, you will come to exactly to the same conclusion. It's order. But there is no periodicity. There is no motif that repeats itself periodically. Of any size, motif of any size that repeats itself periodically. Okay. This is quasi-periodicity in one dimension. What is quasi-periodicity in two dimensions? This is a Penrose type. Penrose is an eminent scientist living in our time, a British, marvelous physicist, philosopher, I mean an amazing scientist, mathematician. He developed the Penrose tiles. These are two rhombi, 36 degrees and 72 degrees. If you join them together, according to some matching rules, you arrive at a tile floor with no gaps, and the rotation symmetry of this tile floor is 5-fold rotational symmetry. How do we know that? Because a man called Alan Mackay, a British crystallographer, also living in our times, he's beyond 90 by now, took this drawing and sent it to a friend of him to shine a laser beam through it. He didn't have a laser beam, to perform an optical diffraction, and voila, 5-fold rotation symmetry diffraction pattern. I did not know, and he published it. I didn't know about this publication. Had I known, life would be easier. And what is quasi-periodicity in 3 dimensions? Well, quasi-periodic crystal. Here is one taken by one of the students at the Technion, beautiful quasi-periodic crystal. Now, let me take you to some. I saw that many of you are theoreticians, so you like mathematics. So I will take you to something amazing in mathematics. It's called the cut and project method. And this method was introduced to our quasi-periodic community by 2 French scientists, Katz and Dunant. And they were very young when they showed it to us in a small conference that we had in Germany. So what is cut and project? It says the following. You can take a high-dimensional space. Can be 2-dimensional space. And make a cut and project onto a lower dimensional space, from 2-dimensional space to 1-dimensional space, and from periodicity, you arrive at quasi-periodicity. Let me show you how it's done. This is clearly a periodic system. Assume that there is a mathematical point at each intersection. And this is the cut. The cuts start at the left bottom at a point, and I sent it in a direction, such direction that tangent of alpha is a Fibonacci number tau. It means that the line that starts at the point will never meet any other point on its way. Never. Because if it met a point, then the tangent would be a rational number. But I sent it in irrational direction. Okay. Now you take all the points inside and project them onto the line, which is a lower dimension than the 2-fold lattice. And now look what happens. Look at the distances from the top to up, go up. There is a large distance, large, large, small, large, large, small, large, small, and so on. Fibonacci rabbit. So we took a periodic structure. You can do it. Mathematicians usually like to work in 6 dimensions, and they make a cut and project onto a 3 dimensions. They select whatever they want, periodic structure in 3 dimensions, cut and project it onto 3 dimensions, and invent new quasi-periodic systems. They can invent as many as they want. Do they exist in nature? Maybe yes, maybe no. But they can invent them just like this. So this is the cut and project. Now, let's do something different. I repeat doing what I did before. Alpha, tangent of alpha is Fibonacci number. Now I bring red lines. The red lines are very close to the black lines, but they do not match. Because I made the red line, the lower red line, meet up there at the point, just one before the top. It meets at the point. I made it this way, and so the tangent of that angle is 11 divided by 7. 11 divided by 7 is the tangent. So what is special about this? This is clearly a periodic structure with very large unit cells. Very large. Here is the unit cell, which repeats itself. Okay? Such materials exist. They are almost quasi-periodic. They have large unit cells, but they are just not quasi-periodic. We call them approximants because they are approximately quasi-periodic. This is a proud set of materials. There are many materials that exist with this structure, and they have interesting properties, and many people study them, study the approximants. Okay, enough of this. And now I will tell you my story. And the story is named Years of Rejection. This is why I call them. In the first years, while I was at National Bureau of Standards, talking about my discovery, trying to convince people that, hey, we have something new here. I did not know what it was, but I knew what it was not, and it was not wind. The reaction was varied. On the one hand, John Kahn, my host, was encouraging. He came to my office time and again. Hey, Danny, this material is telling us something, and I challenge you to find out what it is. He didn't solve the issue, but he was encouraging. On the other end of reactions was my group leader, different person. He came to my office one day, smiling sheepishly, putting a book on my desk of X-ray crystallography. And he says, Dr. Shechtman, please read this book, and you will understand that what you are talking about cannot be. And I said, you know, I know this book, I teach at the Technion. I'm telling you, my material is not in the book. Took the book back, came back a couple of days later, and he says the following, Dr. Shechtman, you are a disgrace to my group. I cannot have my name associated with you. Please leave my group. So I left. Don't faint. It was an administrative issue. Instead of his group, I had to join another group. So it took me a day to find another group that adopted the scientific orphan, and that was fine, no problem. Instead of reporting to his secretary, I reported to that secretary, and life continued. But this is the variation between support to total rejection. And everybody else was somewhere in between. You know, some supported, some were against me. Some told me, you know, maybe you should read the books again. Other people behind my back, I heard somebody say, what do they teach them at the Technion? Don't they know the rules of crystallography? I mean, what is this institute? Okay. Now, during these years, 1982 to 19, this is the year of discovery and the year of publication. I felt uneasy. It was not easy. And if you want to know how I felt, it is something like that. Okay, these were the first 2 years. 1994, publication. Some people started to accept, repeated my experiments, and a lot of commotion started. And until 1987, The main objection came from the International Union of Crystallography, because the tool of choice was X-ray diffraction. We showed them electron diffraction. They said, that's not good enough. Give us X-ray diffraction, then we can talk. We could not do that because we did not have large enough crystals to have single crystal Laue patterns. But in 1987, a colleague of us who died regretfully last year in Japan, he discovered the first stable quasicrystals, those that melt congruently, those that do not change phases until the melting point. And then he could grow large crystals, and he could do it, and French group could do it, and they sent me diffraction patterns taken by X-ray diffractometer. And in 1997, I showed these pictures in the International Union of Crystallography meeting in Perth, Australia. Perth is on the west side of Australia. And when I showed this picture in my talk, the community said, okay, Danny, now you're talking. They formed a committee that adopted quasi-periodic materials into the realm of crystallography and changed the definition of a crystal. This was the second period. Now you think, okay, the International Union of Crystallography accepts, who will object? Well, not so fast, because then there was Professor Linus Pauling. Now, Professor Linus Pauling was arguably the greatest chemist of the 20th century, definitely in the United States, maybe all over the world. He taught us so many things. He wrote the books. He was an amazing person. The only difference between Linus Pauling and God is that God did not think that he is Linus Pauling. Linus Pauling, though, Linus Pauling says one sentence which I cannot forget. He says, there are no quasi-crystals, just quasi-scientists. And 1,000 people clap hands. Because somebody who is not in the field and he has to choose between Linus Pauling, the sun and the sky, and what's his name? Clearly, okay? My daughter came from high school in the United States, and she said, Daddy, is this Linus Pauling that wrote the book that is against you? I said, yep. She said, Daddy, he must be right. I said, no, my daughter, he's wrong. And he was wrong. He was wrong because he did not understand electron microscopy, and I was an expert in electron microscopy. Okay, so he fought us from 1984, the day of the publication, until 1994. He stopped in 1994, 10 years, because he died. And that was the end of objection. Okay, I want to mention a few names who made seminal contributions. Roger Penrose, I mentioned. Ellen Mackay, I mentioned. Ellen Mackay, to remind you, took the diffraction pattern from Penrose style by optical diffractometer, which he did not have. He sent it to a friend. Ian Blech, Denis Gratias, John Kahn wrote the first paper with me. I mentioned John Kahn. Denis Gratias is a French mathematical crystallographer. John Kahn invited him to NBS just to make sure that what I'm talking about is correct, and he helped in the mathematical language of our first paper, second paper actually. W. Levine and Paul Steinhardt came with the tiling model, while Ilan Blech came with joint Icosahedral model, physical model versus mathematical model. All they are important. Now, this is a very interesting graph. And I show it to you because just to give you an impression of the excitement in the field. The year is 1986. It contains a lot of information. It was drawn by hand by a colleague of mine. He brought it to lunch to Zjazd. I confiscated it from him. Otherwise, he would dump it in the garbage bin. But it's important. I'm happy I took it from him. What it is, at the bottom you have the month, January 1986, January, February, March, and so on. Up there goes 1 over n. What is n? N is the number of pages in the bibliography. We hired a secretary who collected all the papers of quasi-periodic materials from all over the world, and she filed them in a computer. And so every page of bibliography may have 20 papers. So if n is 1, then we have 20 papers. If n is 10, we have 200 papers, and so on. And here we have 1 over n. So 0.1 means 10 pages. It means 200 papers. Okay? He counted the papers and marked X in each month. And I arrived there in July, so we see what happened in July 1986. And as a good scientist, he connected them with a straight line. Of course, just to show us that in December of 1986, the number of papers on quasi-periodic materials will reach infinity. And here is the proof. Well, it didn't happen, but the feeling was that it's going to happen. The feeling was that we have to cut all the trees in the Amazon just to make paper to publish our paper. It was an amazing feeling. Okay. While order was, I have 4 minutes. While order was similar to periodicity, now we know that order can be periodic and can be quasi-periodic. I want to answer a question. I started the session now. I asked the first question, and I want to answer it. The question is, why quasi-periodic materials were never discovered before 1982? Why? Is it because they're very rare? Or is it because they're not stable and they go phase transformation? Or are they difficult to make? Or maybe they are made of very rare elements, praseodymium, gadolinium, and touch of zinc? What? Well, are they rare? Not at all. There are hundreds of them. Here is just one page in a list based on aluminum alone, and there are many others. There are hundreds of them. They are not rare at all. Somebody could have stumbled upon one. Are they not stable? Many are not stable. What does it mean? You heat them up to 450 degrees, they transform. But at room temperature, they're stable. You can study them. And then there are stable ones. Many discovered by Ankpen Tsai, died this year. And some people discovered more. They are stable compositions. Okay, that's not a problem. Maybe they're difficult to make, and with my magic hands I prepared one. Not at all. It's very easy to make them. You can make them by casting, by recrystallification, by single crystal growth, by electrode deposition, CVD, PVD, any method you prepare metallic materials, you make quasi-crystal easily. No problem at all. This is not the reason they were not discovered. Maybe they are made of rare elements. Not at all. They are made of iron, aluminum, chromium, copper, titanium. Millions of tons of these elements are used every year. Very common elements. So why is it that quasi-periodic materials had to wait for me to discover them? Now my answer to this question. My answer is the following. Number one, TM. Quasi-periodic materials had to be discovered by TM because crystals were small. And if you took a diffraction pattern for many crystals, you have rings. And you lose the rotational symmetry. You have to look at one. You have to look at one which is small. Transmission electron microscopy will do that for you. So you may ask, okay, great. Why you? I mean, there are thousands of electron microscopists in the world. Well, it's not enough. You have to be a professional. You have to be, you know, the transmission electron microscopy is a fantastic tool. It can give you amazing possibilities to study materials, but you have to know how to do it. You have to put yourself into the space of the crystal and look from within in each and every direction. You have to really know what you're doing. And I was a professional. And there are very few professionals in the world. You'll be very surprised. Very, very few. Especially in diffraction contrast. Phase contrast, where you see atoms, easier. Diffraction contrast, you really have to dedicate years to become professional. Tenacity, okay? Everybody says that you're wrong. But you know that you're right. And then you can stand tall and say, no, I'm right, you are wrong. This is tenacity. And believing in yourself. You can believe in yourself if you are a professional. And this is true for every subject. Become a professional in something you like, and you'll have a wonderful scientific career. But try to be number one. And resilience. You know, my promotions were delayed, and I had to suffer a lot. But everything was okay. Now let me tell you something. We are now 40 minutes on the 100th of a second. Question? Thank you.
Well,
I don't know if you have time.
Professor Shechtman, thank you very much for perfect timing, but it's most important that it was fascinating, beautiful presentation. So now it's time for a discussion. If after this clear presentation, it's really necessary. There is a question here.
You know, the acoustics in this hall is very good, very bad for my ears. I cannot hear what people say on the mic. Maybe, Janusz, you can come here and tell me in your words what is the question, okay?
Okay.
My problem.
So, here is a question. Okay, please.
So, what I was curious, you talked about inorganic materials. Do you also have quasi-crystals among organic materials?
Okay. Do they exist in organic materials? They were not found yet in organic materials.
Another question.
Well, virus capsids are icosahedral. My question is that your systems are alloys, so you can imagine that there could be local density fluctuation, local fluctuation in the composition. Could that be a problem in interpretation?
You know, I don't know of... People try to find some rules, what composition we can use. And there were some predictions made in the early stages. But this composition, this prediction did not lead to new discoveries. What did lead to new discoveries is if you find in a ternary phase diagram an approximant structure which is an approximant near this composition, you may find quasi-periodic material. So it was more trial and error than something that you can predict.
Okay, so we are more or less 5 minutes after the schedule. I just propose that the rest of this discussion of this fascinating subject is during coffee break and later. Professor Shechtman, thank you once again. It's really
Thank you.
fascinating.